My name's Joe Conley. I'm a support engineer with Epic Games. I work closely with our licensees to help them successfully ship their games with Unreal Engine. And today, what I want to talk to you about is the case where you make your game, but the assets you have are too demanding for the target hardware. This is a common occurrence when developers build and test their project on a powerful PC, but don't actually test it on the target device. Some common issues include obviously running out of memory, load times that are too long, and hitches related to garbage collection. So I'll talk to you about ways to address these problems today. We'll talk about 3 ways to avoid and resolve these kind of problems. There's asset reduction, there's optimization for load times, and optimizations for garbage collection. So we'll start with asset reduction. There are many times where the asset, as it was created, is more detailed than it needs to be. Or in other words, it can be optimized in a way to give you 90%, 95, 99% of the quality, but in a way that performs significantly better on the target hardware. So what methods do we have for asset reduction in UE4? When considering different methods of asset reduction, we should think about how effective each method is, but equally important are any potential side effects it might have. So we'll consider 4 methods: reducing polygons using LODs, merging actors and hierarchical LODs, compressing animations, and resizing textures. So first, LODs and polygon reduction. The Unreal Editor has built-in tools for static mesh reduction and LOD creation. In the static mesh editor, you just adjust this. There's a % triangle slider for each LOD, and you can just reduce it to the number of polygons that you want. So in the static mesh editor, you just adjust this slider to where you want it and apply changes. It's really easy. There are similar settings in the skeletal mesh editor. Previously, to use mesh reduction in UE4, it required a license for Polygon. But recently, we created our own quadric mesh reduction that we feel gives you equal or better quality, but with the benefit that it comes included with the UE4 license, so you don't need an additional license for it. For static mesh reduction, you could choose between the two. You can use Polygon or you can use our quadric mesh reduction. For skeletal meshes, we plan to have support for the built-in mesh reduction soon, so stay tuned. In the meantime, you can continue to use Polygon for skeletal mesh reduction. So the above animation shows 5 LODs that were generated automatically. Each is half the number of the previous. And automatic LOD generation uses what's called quadric mesh simplification. So the mesh simplifier calculates the amount of visual difference that collapsing an edge by merging 2 vertices will generate. And it then picks the edge with the least amount of visual impact and collapses it. And when it does that, it also picks the best place to put the newly merged vertex, and it removes any triangles that that would no longer exist without that edge. And it will continue to collapse edges like this until it reaches the requested number of triangles. But it also maintains UVs, including generated light map UVs, normals, tangents, and vertex colors. And because these UVs are maintained, that means you can use all the LODs can share the same light map and the same materials. The high-level settings for controlling the generated LODs are in the static mesh viewer under LOD settings. LOD group provides a list of presets. These can be changed per project in baseengine.ini. And that's under static mesh LOD settings. We recommend that you set up good categories for your project and mostly just use LOD group rather than trying to set the details of every individual LOD. And an important setting here to note is auto-compute LOD distances. So because the algorithm knows how much visual difference was introduced by collapsing each edge, it can use that information to determine what is the appropriate distance that amount of error is acceptable. And so it can automatically calculate the screen size for each LOD. But if you wish to set the details for a auto generation for a specific LOD, you can do so under the reduction settings. So we want to reduce polygons by using LODs because it can decrease the load on the GPU, specifically in the early Z pass, the shadow pass, and base pass. You're drawing less vertices and polygons in each of these phases. What polygon reduction can't do is it can't help with the render thread. Generally, you're not decreasing draw calls. And it has a potential side effect that it can increase load times and memory usage because we need to load the vertex and index buffers for all these LODs. So this requires some extra consideration on the project side to determine if these are the right trade-offs for your project. So which objects should you make LODs for? How many polygons need to be reduced? And how can you quickly and easily test performance? You can use the graphics debugger to find objects that take a long time to do vertex calculations. So you want to set screen percentage to a low value to eliminate any pixel shader cost. And you want to capture and check the cost of each draw call with the graphics debugger. You can do this by setting the RHI GPU capture options to 1 and using profile GPU. The GPU capture options command will output the draw call, each draw call, and the name of each object that draw call was generated from. But it automatically disables the RHI thread. So the results you see here, the draw thread cost is going to look quite high. So you can really only use this for GPU profiling and not for CPU profiling. There are also commands to dynamically change the LOD at runtime. You can use these to profile your cook builds on the target hardware. You can't change the settings for individual objects, but you can get a feeling for the scene as a whole. Next, hierarchical LODs and merging actors. Merging actors is just taking a bunch of separate static meshes in the scene and combining them together into one mesh. It's easy to merge actors in the editor. You just select multiple actors and right-click in the world outliner and choose merge. If you instead select from the window menu under developer tools merge actors, there's a window that appears with detailed settings for the merge. Whichever method you use, the original meshes in the scene are replaced with this merged actor. So you might want to be careful to, it's a little hard to undo that later. So if you're testing out this for your project, you might want to do it on a copy of the scene when you try that. Hierarchical LODs is similar in that it merges meshes, but it only shows it as an LOD for faraway meshes. This does not replace the original meshes in the scene, so it's a non-destructive workflow. You can turn on HLOD on and off. You can turn on and off per level, and there's an editor to adjust settings for clustering and for mesh generation. Hierarchical LOD used to, again, require a license for Simplygon, but from version 4.19 and on, it's possible just to use UE4's built-in mesh simplification tools, and there's no additional license required for those. But you can still choose to use whichever one you want if you do have a license for Simplygon. Merging actors can help speed up the render thread since there are less draw calls to be made. But it's not possible to reduce the load on the GPU without reducing the number of triangles. So this is where you need to use polygon reduction tools to get that kind of speed up. But also, since you lose the ability to call individual meshes, it's possible that you could actually accidentally increase the GPU load if you're not careful, because it could be rendering polygons that are actually outside the view frustum. Hierarchical LOD is basically the same, but you just have the concern that you always have with LODs in that those additional meshes also need to be loaded in memory, so it could increase load times and memory usage. And like a lot of optimizations, it's a trade-off. One thing you need to be careful of here is the HLOD data is referenced by the level. So make sure you have the budget to have this extra data loaded during the time that the level is loaded. And there are two additional cautions here. Draw calls can never actually be reduced unless you merge the materials. So merging objects always, and the other concern is merging objects always generates a new mesh, even if you already previously merged the same mesh in the same orientation. So in order to actually reduce the number of draw calls, you need to make sure that you check the merge materials checkbox when you merge the actors. You can, to illustrate the problem, you can see on the left, there are 3 meshes that were merged without using merge materials. And on the right, you can see that what that translated to in terms of draw calls. And you can see that there's a draw call per material. So if we do the same thing and choose merge materials, we've now saved 2 draw calls. The other thing that you might run into is merging objects always generates a new mesh. This is true even if we've already merged the same mesh in the same layout previously. So if you have these meshes that exist in 2 places in your scene, even in the same layout, if you use actor merging to merge one, and then again to merge the other, you'll end up with 2 separate meshes in the content browser, which is a waste of memory. Don't do that. And it also bloats the package size of the game. So you should merge them once, and you should reference that same mesh in a different place if you want to use it in multiple places in your scene. Blueprint's a pretty handy way to do this here. Next, we'll talk about compressing animation. Animation compression and texture resizing are probably 2 of the biggest ways to lower your memory usage that we'll talk about in this presentation. So if you're running out of memory and you have a lot of animations or you have really big textures, those are areas you're going to want to look at. That's a good place to start. In terms of animation compression, compressing animation sequence is important to reduce overall package game size, and it can be effective in speeding up load times. Each animation asset has a compression setting in the section, a compression section in the settings. Compressing animation sequences is important to reduce overall package game size, speed up load times. It's important to notice that the compressed animation data is used directly. It's not decompressed in memory. So not only are you loading less data, you're also using less memory. But obviously, if you compress too much, it can be noticeable. So we need to choose the compression method that has the best trade-off of quality and size of the resulting compressed data. So animation compression is applied when you import the asset. But if you didn't happen to choose the appropriate animation compression setting when you imported the asset, it's not a big deal. There's actually a compress animations commandlet you can run that will compress all of the animations in your project with the default setting, which you can change in the project settings. You can opt for a different compression or no compression on a per asset basis. There's a checkbox for that. It's the do not override compression checkbox. The compressed ratio and size is shown in the content browser, but I'd also recommend looking at the actual size of the cooked asset on disk and confirming the size in memory with memreport. You can see in the third-person template, just by changing the compression settings from low to high, that actually reduced the amount of animation data by 50%. So it's definitely an area to focus on in terms of optimizing load times, memory usage, and overall game size. There are a lot of different animation compression options, different methods in UE4, and there's a great overview of them in Nicholas Frichette's blog. I have a link here. We have been working with Nicholas to identify areas to improve UE4's animation compression, and he's currently planning on releasing his own animation compression library as a plugin for Unreal Engine on the marketplace for 4.22, and he wants to do that in a way that all Unreal Engine developers can use it for free. Also new in 4.21, animation compression now uses a whitelist of optimal codecs to try avoiding permutations that aren't likely to be chosen. This significantly reduces the number of codecs that we have to evaluate when doing automatic compression, so it's much faster. And on multi-core systems, we also evaluate the different codecs in parallel, and that further reduces the time it takes to run automatic animation compression. Texture resizing is the last asset reduction technique I'll talk about. It's another method to decrease package size, memory usage, and load times, but it can also reduce GPU time if you use lower resolution textures. But obviously, if you resize them too small, it can affect the visual quality of your game. In the texture assets details panel, you can see the original imported size, and there's also a max in-game size. The max in-game size will be the size of the final cooked texture. The other setting you want to know about is LOD bias. If you set this to anything higher than 0, it will remove that number of the highest bitmaps from your texture. But if you set that in the texture asset editor, it actually will affect all platforms. So for multi-platform games, you want to actually set it, if you only want to resize it for a single platform, you can do this by modifying the texture LODs group settings in the platform device profile.ini. And here's an example of how much memory can be saved by reducing texture size. So those are the asset reduction methods that we'll cover today. Next, we'll talk about profiling and optimizing load times. So when loading, there's basically two kinds of possible problems that can occur. The first is that actually reading the data from storage into memory takes too long. And the second is that adding actors into the world and initializing object state takes too long. The latter usually shows up more commonly as hitches during level streaming. So I'll go over some methods of profiling these problems, and then I'll talk about some ways to optimize and fix them. First, on the profiling side of things, you want to start with the stat levels command. This just, there's multiple things you can look at. You want the start levels command, there's dumping load time reports, and outputting add to world timings. The first one that you want to look at is the stat levels command. This will show you a list of the current levels that are loaded in your game, and it will show their current load status. So there's unloaded in red, loading in purple, loaded into memory, but still adding objects to the world in orange, and finally completely done loading in green. You can use this as a quick way to see which levels are taking the longest to load. Once you've done that, to dive deeper into which specific assets are taking too long to load, you want to use loadtime.dump report. And that will get the number of milliseconds that each asset took to load. You can also use, there's a load time parameter that you can use to exclude any objects that take less than a specified amount of time. And there's also a file option, so you can save the output to a file. And then if you wanted to compare that to the previous state, you could use a text diff tool to see what changed. It's important to note that you have to reset the counters between each test. So don't forget to call loadtimes.reset to reset before taking a new measurement. Next, in order to profile the add to world timings, there's a pound define and async loading.h. These will enable you to get a detailed report of the add to world timings. When you do this, it prints out a breakdown of the different phases of the add to world step and how long each one took. In this example, you can see that the move actors and init DSP and init actor physics all took very little time, but the update components took a lot of time. So then you know what is the area to optimize. Next, in the optimization side of things, we'll talk about packaging settings, the order in which files exist on disk, eliminating unnecessary data, asset preloading, and the begin play event. First, when packaging your game, there are two important settings. There's a setting that is called that it combines all of the assets into a single Unreal pack, and that is actually necessary to use the event-driven loader, which is the loading method that we wrote specifically for optimized for consoles. And also, whether or not to compress content can have different impacts on different projects. So you need to test in your particular project on target hardware. Some platforms have dedicated hardware to speed up this decompression, but the platforms have different requirements for how to use the compressed content setting in order to take advantage of that dedicated hardware compression. Some platforms actually require that you check it, and some platforms actually require that you don't, because some platforms use a compatible compression method with ours and some don't, and have their own separate compression that's applied at packaging time. So you need to check the details for each project on the optimal settings there, or for each target platform and for your project. File open order is super easy win for all projects. It just arranges the files on disk in the order that they're loaded. This would be hard to do manually, but there's a simple automated way to do this built into the engine. It's basically you play the game once and you record the order that all the files were loaded in, and then that's saved to a file, and you take that file and you pass it back to the packaging process later, and it arranges those files in the correct order. So the reason that this was originally written was for spinning hard drives. If the files were requested were in a different order than they physically existed on disk, the head would have to seek to each file, which wasted time, and if the file to be read was stored just before the one that you just read, the disk had to rotate around again. So originally that was intended to reduce seek time on spinning hard drives, so you might think it wouldn't be important for flash storage, but for example, if you ran the Elemental demo on flash storage, you can see that without the file open order, it's about 1/3 slower than having it enabled. So why is that? It turns out even on flash storage, you have the file system will read data in blocks, and the size of the block has a large impact on read times. Basically, the larger the block is, the faster you can read data. But if you're reading a lot of small files and the block size is large, then if the files that you are reading in that block aren't ones you need right now, you're doing wasted work. So the optimization has the greatest effect on games where the load order is known. But even in an open world streaming game in which you don't know the order that character meshes and environment meshes will be loaded in, because those character meshes and environment meshes and other assets themselves are made up of multiple files, having those files put together in the order that they will be requested in still has a big impact on load times. So the next topic is removing unused data. You might be confused why there's unused data on in your game to begin with. You may ask, if I'm not using it, well, why is it there? Well, to answer that question, we need to take a step back and remember that Unreal is a general purpose game engine, so it needs to be able to support the needs of a variety of games. And it's also available for anyone to use, regardless of skill level. So we need to make sure the barrier to entry is relatively low. And we also make sure developers coming to the engine for the first time aren't overwhelmed. So this is a very different situation compared to, say, an in-house game engine that's designed to make a very specific type of game and has been used by the same team of people to make that type of game for many years. So when we design features at Epic, we have to make different design choices than you would in that situation. For example, Fortnite is a game that doesn't use any pre-computed lighting, but we can't ship Unreal Engine with pre-computing lighting disabled because anybody trying to use it would just be instantly confused why it's not working. So usually projects that know that they don't need features know to turn them off, and they know how to, or at least know how to find out how to turn it off. So we usually err on the side of leaving commonly used features enabled. and on the side of making it easier for people to get started with Unreal Engine, even if it means there's a little more effort required to get the most performance out of the engine. So with that background, I can tell you another important optimization is removing unused shader permutations. We leave them all on by default so that everything works by default. But if you know you aren't using, for example, stationary skylights in your game, you should disable the shader permutations for them. Same with atmospheric fog or low quality light map shaders. This will also reduce material compilation time and reduce the size of the material UAsset file itself. So an example here of the differences this can make, if you had a relatively simple material like this one, if you leave all the shader permutation on versus turn them all off, there can be about a one-third difference in the number of shaders. There's also some buffers that you might not be using that you can disable. Reverse index buffer is a really easy one. This one is only necessary if you use negative scale. So if you aren't using negative scale, and this might be a really good reason not to use it, you can disable this buffer. The depth-only index buffer does make shadow rendering faster, but if that's not a problem for your particular project and you'd rather have that data back for save on file size and load times, you can disable this. And lastly, tessellations, that is not actually supported on consoles because consoles are generally too slow to run tessellation effectively. So we generally ignore that setting and just tessellation buffers aren't available. So if your project is still not loading as fast as you want, you can try individually loading some assets using the asset manager if you have the extra memory for it. The asset manager is a good system for asynchronously loading assets in the background while you continue to play the game. Our official documentation covers it pretty well, so I won't go too in depth with it here today. One thing I do want to talk about is the begin play event. So one thing you need to be careful about is putting a lot of logic in the begin play event. There's basically two places that you can initialize object state. You can use either the begin play event or you can use the construction script /C++ constructor. You might be aware that the construction script and C++ constructor run before begin play, but you might not be aware that when you actually place objects into the scene, that is, when you're not dynamically spawning them, that C++ constructor and the construction script and blueprint are run at placement time, and that resulting object state is serialized and saved to disk. So there's actually a difference in runtime cost between using the construction script or C++ constructor and using the begin play event. So if you're doing a lot of work in begin play on blueprint, you might want to consider moving the work that you can into a construction script or C++ constructor. One thing I do want to note here is that you need to be careful that the work you do in the construction script /C++ constructor is deterministic. And sorry, this is kind of a tangent, but it's important to mention. So if you were, the reason you need to be careful about this is because the construction script and C++ constructors are evaluated at cook time. And the object state is serialized at that point and stored into a file. So if you were to generate a random number in the construction script and save it into a U property, that resulting U object state will be different the next time you run that. So for example, if you cook a build for release, and then even if you don't change anything about that asset and you cook another build for a patch, that U object state will be different, and the patch tool will say, oh, this asset changed, I need to include it in a patch. And our patching works at the U asset level, so it's going to include the entire asset just because that one random number changed. So that's a bit of a tangent. Sorry about that, but I just want to be careful and make sure you guys knew about the trade-offs of begin play and the construction script and C++ constructor. The last topic of the day is profiling and optimizing garbage collection. So we'll talk about these different topics in order. The problems you can commonly see with slow garbage collection, the basics of the garbage collection system, how to profile the garbage collection costs, and what you can do on the project side to improve garbage collection speed. So usually the kind of problem you can run into with garbage collection is noticeable hitches when the system is in the process of checking UObjects to delete ones that are no longer needed. And if you make your game without once ever considering garbage collection, it's pretty easy to run into hitches that can be as long as even 1 second. So the time where you notice it most is during level streaming because the new level and old level exist in memory at the same time. And since the game is not paused and there's a temporary increase in the number of objects that exist, and also many objects are being deleted at once. So the garbage collection implementation in Unreal is relatively simple. All the UObjects are just stored in this big array. And when garbage collection happens, by default, UE4 will check all elements in the array and delete ones that aren't referenced. So there are two types of costs here. There's the cost of checking each object, and the cost, which is sometimes called marking, and the cost of deleting any unreferenced object, which is sometimes called sweeping. This means it's totally possible to see hitches even if objects aren't being deleted, simply if the number of UObjects in your scene is high. But actually the description on the previous frame could be made a little more detailed. The deletion cost here actually has two parts: detecting dependencies and actually deleting the object. The actual deletion of the object can be distributed over multiple frames. So the cost of garbage collection on the frame that you call it is actually the cost of checking the array of UObjects for ones that are no longer referenced and detecting dependencies. So from this point on, I'll just call those two I'll call detecting dependencies and deletion I'll call the detecting dependencies step deletion cost to keep this simple. One piece of good news I have for you is if you were developing a UE4 game in the past and you had problems with garbage collection related hitches, in 4.16 we actually made garbage collection twice as fast. So it doesn't require any work on the project side as long as you're on 4.16 or later. Also new in 4.20 is the work of deleting objects, that is, calling begin destroy on them, is distributed over multiple frames. So it's a lot harder for this to cause hitches. So profiling garbage collection. There are 5 different tools I'll talk about for profiling garbage collection. The main command is log garbage log. And the name's a little confusing, but this command is saying, I want to change logging settings for the category of logging called log garbage, and I want to see all messages of verbosity log or greater. You can also say log garbage verbose to get even more information. But you can see that it will print out the checking cost and the deletion cost in this way. We also have a command that whenever a hitch is detected, it will print out the timings to the log. It's called stat dump hitches. This is obviously very handy for garbage collection related hitches as well. And one note about build configuration. In development builds, we actually have some additional checking that's run. It's additional verification that's run during garbage collection. So profiling in a test build is going to be your best option here. But you can use no verify GC option on the command line to turn it off if you really need to profile in a development build. But the test build will give you the most accurate timings. You can also use start stop file and stat start file and stop file, and you can open the resulting file with the CPU profiler in Unreal. This is documented pretty well on our website, so I won't talk about it too much here. And you can also enable the pound defines profile conditional begin destroy and profile conditional begin destroy by class. And those will help you profile deletion costs per asset to verify that there is no unexpected behavior there. You can also use, if at any point in the game you just want to know what kind of U objects and how many of each exist in your scene, you can use the obj list command. And you might notice here that there's quite a few bool, float, and object properties here. Well, let's focus on bool and float. So one thing that we've seen before is that heavy usage of macros blueprint macros in specific lead to a lot of U properties existing at runtime and thus slow garbage collection times. But the blueprint stats plugin can help you find blueprints with the most U objects. So now I'll talk about what you can do to actually improve the garbage collection times. There's a lot of different things you can do on the project side to optimize for garbage collection, and I'll talk about each one. But the thing that's going to have the most impact is the size of your levels. When your levels are large, that means that there's just a lot of U objects to check for garbage collection. And it also means that there's more to delete when streaming the level out. So if you can split your levels into smaller pieces, it's going to be a lot quicker for garbage collection. But it can be more difficult to work that way. So it's important to profile at an early stage to determine if this is something that will be necessary for your project. One common pattern with a lot of games is that there are systems that are loaded into memory at startup and then never unloaded. They aren't specific to any one level, but they exist throughout the lifetime of the game. Since any objects that share the lifetime of these systems are never deleted, we can safely avoid checking them for garbage collection. And the garbage collection system in UE4 has a way to, it has the concept of U objects that are loaded and never unloaded. We call them permanent resident objects. If you can avoid, checking these objects during garbage collection, you can save a lot of time. But there is the requirement that these objects are all loaded by the end, by the time that pre-init is finished. So setting this up is really easy. There's just two settings in project settings for this. They're maximum object count not considered by GC and size of permanent object pool. But you don't actually have to do any of the work of finding out these numbers for yourself. The system will tell you if they're not set correctly. All you need to do is set the max object count not considered by garbage collection to 1 and the pool size to 0. And then in the log, it will print out what the correct size and number should be. And so then you just take those numbers and put them back into the settings. So it's really easy. It's definitely worth taking the time to do that. For example, the savings you can get from this is pretty large. For a sample project, this actually reduced the cost of checking for garbage collection by 20%. So up until now, we're talking about garbage collection in terms of individual objects, but the reality is that objects really aren't that independent all the time. There's a lot of objects that have exactly the same lifetime. So clustering is one way to speed up garbage collection checking costs, but it doesn't affect deletion costs. So clustering is just considering several objects together for garbage collection to reduce the total number of objects that you're checking. We have two kinds of clustering. We have actor clustering and blueprint clustering. Actors can be put into a cluster with the level that they belong to and just removed when that level is deleted. There's a setting for this. It's enabled by default for static meshes and reflection captures, but you can also try enabling it for other objects and seeing how it works. Clustering runs when the actors are added to the scene, so you can't add any references to those objects later. So for example, if you load up a level that has a static mesh placed in it, that you want to have clustered with a scene, but then you later load a sequencer sequence that references that static mesh, that reference was not known about at the time that the static mesh was created, so it can't be clustered with the level. But in development builds, there's warnings that pop up if you accidentally break that rule, so it's pretty easy to tell. Blueprints tend to have a lot of U objects that share the same lifetime, so clustering them together with the blueprint can be quite effective to speed up checking cost. We enabled it for Fortnite, which significantly reduced garbage collection mark time. It reduced it from about 66 milliseconds to 22 milliseconds on PS4. We also made a bunch of performance improvements for the cluster verification code that's used in development builds. And we also started work recently on a technique that moves clustered objects into the disregard for GC pool for a faster early out. So here's an example of the impact of actor and blueprint clustering. In this example, actor clustering reduced garbage collection times from about 26 milliseconds to about 15 milliseconds, and blueprint clustering reduced the times from about 43 milliseconds to about 34 milliseconds. So one thing you can do to decrease garbage collection times, one thing you can always do is just decrease the number of U objects. And we've identified a number of areas that are easy wins for this. I mentioned a little bit earlier, but blueprints can tend to contain a lot of U properties like bool or float properties. And we've seen before that heavy usage of macros led to a lot of U properties existing. For each use of a macro in a blueprint graph, any local variables, which include the inputs and outputs, actually create a U property to represent them. So using lots of macros with lots of inputs and outputs in many places will increase the number of U objects that exist while those blueprints are loaded. But that per instance cost of macros is not true for blueprint functions. So we definitely recommend that if you have blueprint macros with a lot of inputs and output variables that are used in many places, that you convert them into blueprint functions instead when you can. Again, the Blueprint Stats plugin will help you identify the blueprints with the most U objects so you know where to focus your efforts. Blueprint Nativeization is another tool we have that converts blueprints to C++ during the cooking process, and that can speed up execution. But it also has the positive side effect of reducing the number of U objects to a degree. It's not as much savings as converting blueprint macros to blueprint functions can be, but you can save a little bit of time, and every little bit counts when it comes to performance. So these are the different ways we talked about to decrease garbage collection time. And that was the end of the garbage collection part of the talk and the end of my slides altogether. So thank you for listening. I hope this helps you with your projects. And thank you guys for listening.